Welcome everybody to the Christmas lecture of Audio Engineering Society UK section. So it is our great pleasure to have here tonight Huseyin Hacıhabiboglu give talk on spherical microphone arrays. Huseyin got his Ph.D. From Queen's University of Belfast, and then he spent a few years at University of Surrey, and fortunately for us, then he transferred to King's College London, where he worked with me and Sudesena. Some of you might be familiar with my previous talks. I gave a couple of talks here related to new immersive sound technologies, and Huseyin is one of the inventors with me and Senna of that. So I'm finally happy to be able to introduce him to everybody in this society too. Huseyin is currently Associate Professor of Signal Processing at Middle Eastern Technical University in Ankara and Head of the Department of Multimedia Informatics, and at the same time Associate Editor of IEEE Transactions of Audio Speech
language processing.
Language processing. The title keeps changing, and it's IEEE and ACM transactions, etc. Well, anyway, so yeah, I'm going to hand the microphone to Huseyin, and thank you all for attending for a very interesting talk on microphone arrays.
Okay. Hello and welcome. Thank you very much, Zoran, for inviting me and the whole AES British section for organizing this talk. It's a great pleasure to be here, back in King's College as well, which was my home for 3 years or so. So today's topic is going to be on spherical microphone arrays. I'll talk about the theory. I'll talk about the methods and applications, and I'm going to present some of the results which we recently obtained with coherent sources. We used these microphone arrays specifically for analyzing sound fields, extracting audio objects, for instance. Before we start, some shameless self-advertising. I guess that's part of the game for every presentation. Sorry about this. A little bit about my university. It was founded in 1956. It's the top research university in Turkey. We have 2 mainland and 1 overseas campus. We have approximately 28,000 students. It's a huge university. 791 full-time and 225 teaching staff. We do research in different domains, but mostly in physical sciences, engineering, and some humanities. So everything is covered except for medical science. And ODTÜ Teknokent is one of the most successful research parks in the country. So going a little bit more about my department. It's part of Graduate School of Informatics. We do research in audio signal processing, as you will hear today. Parallel computing, computer vision, motion, understanding human motion, deep learning, musical interaction, artificial and virtual realities, and game technologies. We have 3 major research groups. Spatial audio research group, that's my research group. Computer vision and remote sensing, and entertainment computing and interactive systems. We are affiliated with NVIDIA Deep Learning Institute, so we do quite a lot of deep learning as well. On all of the topics that we do, we try to employ those methods. I'm trying to stay a little bit away from deep learning at the moment, because I don't like the idea all too much, but eventually I'm sure I'm going to go that way as well. And we are active in national and international projects. So my research group, I founded the group in 2013, so it's relatively new. It's the first and only dedicated research group on spatial audio in Turkey. And current research focuses on object-based audio, multi-channel systems, acoustic scene analysis and synthesis. So we do quite a lot of work on language processing to go from free text descriptions to synthesis of auditory scenes as well, acoustic scenes as well. Microphone arrays and game audio. There's 1 PhD student, 7 master students, and 1 BSc student who is there as an intern actually to work on these topics. And we have a specially designed audio and acoustics lab with state-of-the-art audio equipment located in this building over there. So, outline of my talk today. I'll first talk about the theory of rigid spherical microphone arrays. And then I'll move on to methods related to rigid spherical microphone arrays, then theory about open spherical microphone arrays, and then methods which are applied in open spherical microphone arrays. Then I'll talk about applications and summarize. So just a little introduction about spherical microphone arrays. Now they're getting more and more mainstream. You see more commercial examples of spherical microphone arrays. I'm going to talk to you about some examples. I'll give some examples. And it's a hot research topic for the past 2 decades. They provide the opportunity to capture the whole sound field in 3D, and that's a big thing. There are two main types, open and rigid microphone arrays. There are some hybrid arrays which combine these two concepts as well, but they are more, research grade, so to speak. And different theoretical formulations of the same problem is possible. So they are used in a variety of settings: sound source localization, sound source separation, spatial audio. If you haven't heard about it already, there'll be a lot of talk about object-based audio in the near future. And obviously, higher order ambisonics is possible with spherical microphone arrays. And acoustic applications. There are people working on near-field acoustic holography to characterize sound sources using spherical microphone arrays as well. But as far as my research group is concerned, we are interested in audio aspects, recording audio scenes. That photo is from a recording that we made in Ankara in March. An amazing quartet by the name of METU quartet. They allowed us to record their rehearsal. And we had a lot of microphones apart from the Neumann and the Eigen mic, which you see here. And we had microphones which are recording the instruments separately as well. So the idea is to to record the whole scene and extract all of these musical instruments, all the players, as well as the acoustic software environment, and if possible, encode them and send them separately or archive the whole thing in a much more easily reconfigurable, flexible format. That is what object-based audio is about. So the algorithms which I'm going to be talking about are tied strongly to object-based audio aspects of spherical microphone arrays. So let's start with rigid spherical microphone arrays. Unfortunately, the theory involves a bit of maths, but I'm going to try to explain these things in a more easily digestible manner. And so, as with Fourier transform, you have basis functions for functions defined on the sphere. And these are called spherical harmonic functions. You may know these functions from higher order ambisonics for those of you who are involved in those kinds of systems. And you see here 2 parts mainly. One is a normalization term, that's the ugly looking part. And the second part, which is a combination of associated Legendre function, P sub n cosine theta, is one part. And the other part is a complex exponential, e to the power I m phi. And we're using this convention for the spherical coordinate system. So, and we are going to use this function to express functions defined on the sphere. And when I say functions defined on the sphere, obviously I'm talking about the pressure distribution on the sphere, which we record by using rigid spherical microphone arrays or open spherical microphone arrays. And the relation between the degree m and n is given as this. So if you have an order m, it should be less than n. So a little bit more demonstrative example about spherical harmonic functions. You see for different degrees and different orders the spherical harmonic functions. This is a special projection which is normally used in maps. It's called Moll-Weight projection. And basically, this part of your map maps exactly to this part. So this is 0, 2 pi. So it's periodic over the whole sphere. And you see that as you increase the order, the basis function that you're using fluctuates more, its frequency is higher. So you're able to capture more and more details about the pressure distribution on your spherical surface. And you see that you can capture different patterns as well by using these functions. So 3 properties. Again, I'm going to skip things a bit, not to bore you too much. Orthogonality, just like any other proper basis function, you would have this property hold, which just says if you have spherical harmonic functions of different degrees and orders, their product integrated over a sphere will only be a Kronecker delta or a single impulse when the orders and degrees are the same. So that's one of the properties. Completeness says if you multiply 2 spherical harmonics at different directions and sum them, well, using an infinite double sum as in this case, that will give you an impulse on the sphere, a single peak on the sphere. And spherical harmonic addition theorem is a useful theorem. That's why it's there. It's just a multiplication of 2 spherical harmonic functions at different directions. Will give you a closed form. This summation is going to give you a closed form solution with the Legendre polynomial, a normalized Legendre polynomial. So please accept my apologies up front about the amount of maths, but I'm going to give you more concrete examples towards the end of the talk. So there is another property, Christopher's addition formula, which just relates a finite sum of Legendre polynomials to a difference expression, which is the difference of 2 Legendre polynomials. By using this together with our earlier properties of spherical harmonic functions, we end up with a pretty ugly looking expression like this. But that is interesting in a way that it provides you a function on the sphere which gets more and more sharp. So, for instance, think about, I need to ask the question right now, how many people know the term beamforming? Okay, so just a little bit of information. Your regular microphones, like your omnidirectional microphone, for instance, has a directivity which is constant for all directions. Your cardioid has a certain direction, the direction which is looking. And you may define second-order microphones. You may have super-directional microphones, which, as you know, are long microphones which you position at the sound source. Now, the process which goes on behind your enclosure of the microphone is a combination of different signals from different capsules which give you that directionality. And that is called beamforming. You can do it digitally as well. So you see here that if you increase the number of terms in your finite sum, you end up with a beam which gets sharper and sharper. So the first one shows you n equals to 1, which corresponds to a cardioid pattern if you plotted it as a polar plot. And if you increase the number to 10 or 100, you'll get sharper beams, which you can capture the sound field with. So how are these functions useful? These functions are useful in representing any function defined on the sphere, any continuous function defined on the sphere, by a more compact set of coefficients, just like Fourier transform does. So here you see the function f theta phi defined on every point on your sphere being represented as an infinite sum of terms which are which will consist of spherical harmonic decomposition coefficients, SHD coefficients, and spherical harmonic functions. And these coefficients can be calculated by multiplying your function on the sphere with a spherical harmonic function and integrating it over the unit sphere. Now, computers are good at some things, but not good at some other things. Integration is not one of the things that computers can do well, at least at a symbolic level. So the plus, you will never have a microphone array, an actual microphone array, which will allow you to record the pressure on each and every point on a sphere. You will have to use a discrete number of microphones, 30, 60, 100, but it will always be a certain number of microphones on the sphere. So in the end, you end up calculating that spherical integral using a numerical integration formula. Say you can use many different schemes for this, but the general form is this. So you sample the pressure on your spherical surface by using microphones. You measure the pressure on the microphone, and then you just calculate your double integral, that's integral on the sphere, by using spherical quadrature. Any spherical quadrature would do in theory. But there are some requirements. First, as far as spherical harmonic functions are concerned, first you need to preserve the orthogonality property if you want to do anything useful with these functions. And secondly, numerically obtained SHD coefficients should converge to the integral which they are obtained. So unless you have two results which agree somewhat with your analytical expression of the integral and the numerical result that you get, you're not doing something useful. So these should also agree. So these two things are important. As far as actual microphones are concerned, microphone arrays are concerned, you would have only a limited amount of options to have that kind of nice properties. Say the first group of sampling is uniform. You would have tetrahedral, which consists of 4 microphones. You obviously all know the sound field microphone, the MBO or tetra mic, all the sound field microphones over there, first order Ambisonics microphones over there. And you may also have a truncated icosahedron, Lebedev quadrature, etc. So you may know about truncated icosahedron as a sampling scheme from EigenMic. I don't know how many people know about EigenMic. Okay, 2, 3. Okay, so I'm going to show you a photo of the microphone itself. And I'm sure you're going to see that kind of a microphone later quite a lot, because it's one of the key components of object-based audio, which is taking off around these years. So one important thing is that sampling, as in sampling time domain signals as well, causes spatial aliasing. So you need to make sure that that doesn't happen. So that's one key important point. And you can limit aliasing if the number of points that you get pressure samples on your sphere is greater than n+1, which n is the maximum number of spherical harmonics which you're trying to calculate from your microphones. By the way, we haven't yet made any assumptions about whether we use rigid spherical microphone arrays like EigenMic EM32 or an open microphone array like Soundfield or MBO or that kind of open spherical array. So one of the easiest way to demonstrate the use of spherical harmonics is by showing how you express a plane wave. Plane wave, as you know, is the simplest wave that you can get. One of the simplest waves. You have the point sources and plane waves, obviously, and everything in between. But it is demonstrative to look at how things work as far as spherical harmonic functions are concerned. Here you see a plane wave incident from the direction theta sub p, phi sub p, and you can express that plane wave by using a combination of spherical harmonics, weighted spherical harmonics. Now, in classical literature, looking at the sound source localization using classic methods in signal processing, it is not easy to separate the frequency-related components from the direction-related components. So they are, as you see in e to the power I k dot r, are inseparable. But in the spherical harmonic domain, you're able to separate the frequency-related term as a Bessel function and the direction-related term as a spherical harmonic function, which is the main good thing about spherical arrays, which will give you some additional insight into the analysis of the sound field problem. So if we have, by the way, this expression is true for free fields. So if you position microphones in a spherical constellation in free field, then these are the spherical harmonic decomposition coefficients that you get, A sub nm. Okay, so if you use a rigid spherical array, what we know about rigid objects, we know that on the surface of the rigid object, the particle velocity should be 0. You cannot move a rigid object. So there is no movement on the sphere. You can measure pressure, but particle velocity normal to the surface will always be 0. By using that property, you can express the pressure on a rigid sphere by using this expression. I'm not going to go into details of how you obtain that. You just calculate the particle velocity and set it to 0. But that's a different function, B sub n kr. Now, right now, those probably didn't mean anything, but the next one shows these functions. So on the left, you have the free field situation, where you have J n kr, spherical Bessel function, and on the right, you have B n kr. So this is your rigid spherical microphone array, and this is your open spherical microphone array. Now, what do we know about those functions? They, for sure, go to 0 quite a lot. We can see at many frequencies, they go to 0. So any term that we calculate, any spherical harmonic decomposition that we calculate using those functions are going to go to 0 at some frequency, and at many frequencies, really. And when you look at the one on the right-hand side, you see that these functions only go to 0 when we're at 0 frequency. At very low frequencies, you have very low values. So a little important side result is that BNKR, the rigid spherical microphone, has a 0 only when KR is 0. So you are operating at DC, or 0 frequency. So point sources are similar. I think I'm going to skip this one. No need to talk more about this. But here is a result which is kind of linked to higher order ambisonics. In this situation, you have a plane wave, something similar to this figure that you see over here, impinging on a spherical object. The size in this simulation is conveniently selected as the size of the EigenMic EM32 microphone. And if you know the spherical harmonics, spherical harmonic decomposition coefficients, then you are able to reconstruct the sound field. Actually, this is what higher order ambisonics does. It is able to reconstruct the plane wave field by extrapolating from the spherical harmonic decomposition coefficients that you can calculate from the microphone signals which you obtain from your microphone array. But there is one catch. If you have lower and lower order, say when n equals to 3, for instance, your extrapolation capability is much less. You are approximating the field much better if you use a higher number of components. Say, for instance, in this case, it's a 60 centimeter by 60 centimeter square. Whereas with n equals to 3, which is your typical higher order ambisonic setup, maybe 4 or 5 would be achievable with microphones which are in the market today. But that is all that you can achieve is the sound field in a region which is at most, say, 10 by 10 or 15 by 15, that sort of area. Okay, for cases where a finite number of measurements are available on the sphere, the spherical harmonic coefficients and thus the sound field in a limited area around the sphere can be obtained. So you record the sound field and then you can extrapolate. So for this reason, different microphone array designs were proposed. Here are some examples. Visisonics Corporation, that's an old design, by the way, dating back to 2006, I believe. It was a spin-off from University of Maryland. It has 64 microphones on it, on the sphere, and the highest spherical harmonic decomposition coefficient that you can get has an order 7. DTU has a different array that's more experimental, and it has 52 microphones. The photo on, at the middle is from our lab. It's Eigenmic EM32 that also allows recording higher order ambisonics. It has 32 microphones on the sphere. Then another experimental grade microphone from Maryland. And another one, a much cheaper spherical microphone array, which I believe is going to be released or has already been released within this month. It was a Kickstarter project. A company by the name of Zilia is producing this little microphone. It has a really nice software which allows you to record instruments which are performing together separately by carrying out beamforming. So they can do some source separation as well. And apart from that, obviously we are in an age where 360 video is quite common. So you can record the video and you would obviously want to add some 3D immersive sound on top of that as well. So companies like Nokia and Facebook are into spherical microphone arrays, rigid spherical arrays. Facebook has two designs, X24 and X6. Unfortunately, these numbers refer not to microphones, but to cameras on the device. So with the X24, you have 8 capsules, and X6, you have 4 capsules. It's a tetrahedron on the sphere. So it's kind of regrettable actually that they didn't put audio at the center stage, but anyway. So Nokia also, I read a couple of days ago that Nokia decided to drop the product for some reason because it was too expensive, $50,000 or something like that. It could record and store 360 video. And another Chinese company by the well, it was a Kickstarter project, so I don't know the name of the company, but the name of the device is Sonicam. So they claim that they can get up to third order spherical harmonics with their spherical design. So methods which involve rigid spherical arrays. So let's first talk about something which we all agree about, sound fields inside rooms or in free field. Simple sources. You may have point-like or plane waves, point-like sources or plane wave sources. These are the basic components which make up the sound field around us. When you have more than one source, we typically assume that the room acts as a linear combiner, so it combines everything in a linear fashion. And it's time invariant, although it isn't. We assume that it is time invariant, so it doesn't change in time. Acoustic diffuse fields refers to the case where you have multiple plane waves with random incidence directions. That is what happens at the later tail of your reverberation. So you may assume that incidence of plane waves are random from all directions. And then in enclosures, you have direct path components from multiple sources. You have coherent specular reflections from surfaces, like those big reflectors. As well as, there is no diffuser here, but you may have diffusers as well. You probably have diffusers in your studios, in your labs, or in concert halls. You see those type of reflectors. So that was missing from the terms which make up the sound field in enclosures. So the question is, if we can reasonably well approximate such a sound field by using a finite number of plane waves, then we can go from there to a spherical harmonic decomposition expression, which would allow us to separate frequency-dependent characteristics from direction-dependent characteristics and analyze the direction-dependent characteristics of audio signals separately, which would tell us about the directions of sound sources, the properties of the room acoustics, etc. So you have a single recording which would tell you about the room acoustics, which would tell you about where the sources are, and in some cases the distances of sources. So that is something which is quite useful, especially in applications which involve virtual reality or broadcast. I'm talking about the upcoming standards, actually. So here you see a finite sum of L plane waves. Now, if we were in the wave number domain, it would be a combination of complex exponentials with complex amplitudes, alpha sub L, which are again frequency dependent. And if we go to SHD domain, then we can separate the frequency dependence as well as the direction dependence. And this result is relevant for open spherical microphone arrays. You have microphones which are suspended in air without any object to scatter the incoming sound field. And if we talk about rigid spherical microphone arrays, it is possible to find out about how the sound field acts in the absence of that spherical object that you put into your otherwise undisturbed sound field. And you can factor that out by dividing your spherical harmonic decomposition coefficients by B sub n kr and multiplying them by J n kr. So let's assume that you have a rigid spherical microphone array and you want to obtain a directivity pattern that you wish. Okay, so you have a single recording and you would like to eliminate one of the sources from your recording. In a typical scenario, you will not be able to do this. You would normally need to, well, let's say you have a cardioid microphone. The null of the microphone is exactly at the back. So you need to turn the microphone away from the source to reduce its effect on the overall mix that you record with your microphone, right? So for signals recorded using rigid spherical microphone arrays, it is possible to have a single recording which at the post-processing side will allow you to get rid of some sources or amplify some other sources, amplify some other directions. And that is, again, what is called beamforming. Okay? So beamforming is, well, let's say you have a directivity pattern that you want to achieve. You would like to get rid of the speaker that is me, and you would like to position the 0, which corresponds to my position, the null of your directivity pattern in my position. So it is possible to design such a directivity function, and it is also possible by using the microphone signals which you obtain from your rigid microphone array to synthesize such a microphone directivity pattern, which is a big advantage of rigid microphone arrays, rigid spherical microphone arrays. And this is done, okay, I'm not going to go into details of this, but it is done by multiplying your microphone signals by a steering vector, which will give you the directivity pattern that you wish for. So this way, for instance, you can design directivity patterns which have any property which you desire, but these are two examples. Maximum directivity factor. You're just making your beam pattern more and more directive towards the look direction. That's the one on the left-hand side. As you increase n, you see that it's getting sharper. The beam is narrower. And on the figure on the right-hand side, unfortunately, the order is different, so please don't get fooled. So this is n equals to 1, n equals to 2, 3, and 4. So this will allow you to get rid of whatever is in the back of the microphone from your mix, from your recording. So that is maximum front-back ratio directivity pattern. So when more than one plane wave is present, we have the situation where there is an addition of spherical harmonic decomposition terms. And this results in, if we can carry out an infinite sum, that is, if we have infinite number of microphones on our sphere, we can get a really nice peak which shows the direction of the sound source. So that is good, but again, we live in a non-ideal world. We only can use a finite number of spherical harmonics. So although this could be possible in an ideal world, we will not be able to get it. So what we will get is something which is a truncated version of it, because we will only have a finite number of spherical harmonics. We will get, for instance, with eigenmic, we will get up to 4. With other designs, we will get up to 3, 2. Okay, with sound field microphone, we get up to 1, which is your cardioids, your figure of 8s, basically. Your figure of 8 patterns are, or bidirectional patterns, are your first order harmonics, spherical harmonics. Okay, so the main difference is that in this situation, you have a peak which is not an ideal impulse, which is not an ideal peak, a discrete peak, but a function which is spread on the sphere. Okay? Which means you cannot really represent your sound field quite as easily. So, in short, we're going to come back to this, but in short, you can use both open and rigid microphone arrays within the spherical harmonic decomposition framework. There is no one holding you, but open spherical microphone arrays do not provide the same advantages as rigid spherical microphone arrays. They are bandwidth limited by the way that the spherical Bessel function is having multiple zeros. And a more suitable framework for open spherical microphone arrays is acoustic intensity. So, again, I'm sorry there'll be a little bit more math, but in the end, you're gonna see some more practical results, which tie up nicely with object-based audio. So, acoustic intensity is a vectorial quantity indicating the net flow of acoustic energy through a unit area. So, if you have a monochromatic sound field, you can calculate the time-averaged complex intensity at a point x in 3D space by just integrating the product of pressure and particle velocity, complex conjugate of particle velocity, in a single period. Okay? And that would give you the time-averaged active intensity and time-averaged reactive intensity. We're going to come back to this. And here, P is the pressure and V is the particle velocity. In many different contexts, people also use the letter U for particle velocity, but it doesn't matter too much within this context. So the integrand is called the instantaneous acoustic intensity. So we don't do any time averaging on the signal that we obtain. And the real part of this integral refers to, this term refers to the propagating energy, or propagating plane wave. And the reactive part, the complex part, corresponds to the stored energy. Say, think about the standing waves in a room. Those will correspond to the stored energy. You may not always have propagating energy. You may have stored energy as well. So for those of you who are from electrical and electronic engineering domain, these correspond to your capacitors, your inductors, the reactive term. Okay? And the propagating energy refers to your resistive term, if you like. That's the real part. So a single one, but in two different versions of one of the fundamental equations of linear acoustics is related in this context. So time derivative of particle velocity is related to the negative gradient of pressure. And this relation can be represented in frequency domain as well, quite easily. So these can be used as a starting point for further analysis. So if we consider a sound field due to complex monochromatic plane wave, a single frequency, okay, that's your sinusoid, single oscillator creating a single frequency, incident from a given direction, and with the wave vector kx, ky, kz, the associated particle velocity field is quite simple. It is just one simple constant multiplied with pressure and with the same direction as the propagation of your plane wave. And you can calculate the active intensity, instantaneous intensity, as you see in here. And one thing which is striking about this is that it's not dependent on time. So you have pressure, which is a temporal function, which fluctuates. You have particle velocity, which fluctuates. But in this case, active intensity, instantaneous intensity, is independent of time. It's a single vector showing the direction of propagation. So there are different methods of measuring active intensity, instantaneous or active or complex as well. So the first method is called the PP method, and the second method is called PU method. PP method is approximating the derivative, spatial derivative of your pressure field by using multiple microphones. In the uniaxial mode, 2 microphones only. And PU method is measuring the pressure and uniaxial particle velocity separately. So for the PP method, you have Brillouin-Pierre type 3599 as an example. And for the PU method, you have microflown PU family. These microphones, the microflown probes, work in a very interesting way. They have 2 wires for measuring particle velocity, and current is flowing through those wires. And because of wave propagation, there appears to be a temperature difference between those 2 wires. And in that situation, they're just measuring the conductivity of those wires, because when temperature changes, conductivity changes, and they're able to infer the uniaxial particle velocity from this difference. So you can extrapolate this to 3-dimensional case. The PP method can be extrapolated, say, Onosaki tetraphone, grass type 56. And for PU method, microflown has a special probe called microflown USB. These are microphones which are used in more acoustical applications, so not so much in audio, but they can be used in audio as well. But that's just not the company's aim, so to speak, to extrapolate their results to audio domain. And in any case, these are very expensive probes, so probably, even if they wanted to enter the audio domain, they would have fierce competition from other microphone manufacturers anyway. So, for those of you who are familiar with wave field synthesis, this is an equation which is also linked to wave field synthesis, which tells us if we know the particle velocity and the pressure, particle velocity normal to a surface, and the pressure on that surface, we can find out about the pressure, about the sound field inside that volume enclosed by that surface at every point, which is a fantastic result. If you think about sound field reconstruction, it is a fantastic result. It results in wave field synthesis, which, the ideal case of wave field synthesis, let's say, because in the case where you have a planar loudspeaker array, that's a different story. But what this equation is saying is that if you integrate this term, I'm going to come back to this term in a minute. If you integrate this term over the surface S0, it will give you the pressure inside that surface, in the volume which is enclosed by that surface. So here, some of the terms we already talked about. V sub n is the particle velocity which is normal to the surface. G is the Green's function, which is your typical monopole, for instance, a point source. And here you have the spatial derivative of Green's function with respect to the vector which is normal to the surface. It is shown with a red arrow in the figure. And then you have the pressure on the sphere as well. So if you, in some way, can calculate this integral, you can then go and find out about the pressure inside this volume at every point, which is, again, in an ideal world, obviously. In the context of microphone arrays, there is nothing like an ideal world, unfortunately. It would be nice, however. So just jumping to some results without going through all the intermediate steps. I've shown in a paper in 2014 that it is possible to find out about the particle velocity at the middle of an open spherical array by using a finite number of microphones, by using the pressure on the surface only. You don't need the particle velocity. You don't need to measure the particle velocity normal to the surface. So that's a pain, because if you wanted to have an open spherical microphone array which you want to measure the particle velocity normal to the surface as well, then you would need many of those microflow sensors or some other way of measuring particle velocity. That's not a reasonable requirement, I think. And as with the earlier results which I showed, you can approximate that integral by using a finite number of points on a spherical surface. So for this, you need to sample the pressure at Q different points. Again, your selection of those Q points is important. You need to pick a set of points which would give you a good approximation of your integral on the surface. So if, in addition, you also measure the pressure at the center of the sphere, then you're done, because you have the pressure. You can calculate the particle velocity, and quite accurately as well. And you have the intensity, which comes out as a result, which will allow you to analyze the sound field. Energetic analysis of the sound field will be present in your intensity measurements. So again, many different quadratures are possible. Uniform quadratures, tetrahedral, octahedral, cubic, icosahedral, dodecahedral, different designs. Sorry, this should be 20, I'm sorry. So there's one more over there. Then Lebedev quadrature, Gauss-Legendre quadrature. There are many different constellations which would give you good results. And here are some examples, some of which you know. The sound field microphone is the kind of like the granddaddy of open spherical microphone arrays. Obviously, Gerson didn't call this open spherical microphone array. And I guess sound field is a much more beautiful name for the device itself. But anyway, so DPA has its own version. Sennheiser has recently released Sennheiser MBO. They're now distributing it, I guess. Then the fourth one is an actual open spherical microphone array, which has omnidirectional capsules. And that was developed in our lab. We 3D printed it and positioned DPA capsules on the structure, on the plastic structure itself. And then the acoustic camera, which was the front face of this talk, for some reason. It's actually, yes, it is a, well, by definition, it's a spherical microphone array. But at the middle, you have the spherical structure, which acts like a scatterer, which means it's neither open nor rigid. So it's right at the middle. So it's open and rigid microphone array. So methods with open spherical microphone arrays. A little bit about W disjoint orthogonality. If you have two speakers, human speakers, not music, I'm not talking about music, that's a different story altogether. You have two speakers and you record their voices. If you look at their short time spectra, they will be substantially orthogonal. They will not occupy the same time frequency bins. So if you multiply these two spectrograms, so to speak, you will get 0 in the end, or something quite close to 0. That was a result which was obtained in 1997 by people who were then at, okay, I don't remember the university, but that was a very important result. And it is being used in many applications which use sound source separation, especially geared towards speech separation. So this is related in intensity-based sound source localization. The reason is if you have multiple sources in a single time frequency bin, they're going to show a different direction. It's just going to show a direction other than one of the directions, either one of the directions. So you cannot obtain back the original directions exactly. So if you assume that you have two speech sources which may be active at the same time. They may not be conversing. They may be trying to get their voices heard, if you like. And in that situation, you can still separate these sources or find out about their directions of arrival. That is what DOA stands for, by this assumption. So here is one simulation example by using the array which I showed you, the array which we developed in our lab. As you increase the reverberation time from 0.17 seconds, which is pretty reasonable for your living room perhaps, to 1.19 seconds, which is probably reasonable for a small recital hall maybe, okay, or a lecture theater like this one. You see that the effect of reverberation is a buildup of spurious peaks which are distributed all around. That is what I was talking about when I said diffuse field. You have random incidence from all directions. But in this case, there is random incidence plus the direct sound. That is the direction of the sound. Here, the red line shows the actual direction. And the peak of the histogram that is shown is the direction inferred by the intensity-based method, active intensity-based method. And in real-life conditions, your microphone capsules will have noise and you will not have ideal situations ever. But even in that situation, if you record two sources, for instance, two concurrent sources, you are able to infer their directions by using maximum likelihood. So you can get, if you know the probability distributions of individual sources, you can get the source directions by looking at the overall result. So if a dominant direction of arrival can be determined for each time frequency bin, spatial filtering or virtual beamforming can be used to separate sources. So when I talked about recording a sound field using a rigid spherical microphone array and post-processing to get any directivity you want, that was based on spherical harmonics exposition. Now I'm talking about a time frequency analysis of the signal and using virtual beamforming, which is applied as a mask on your time frequency representations, your spectrograms, to get the directivity pattern that you wish, without even recording the sound field using, say, a cardioid, a hypercardioid, or whatever microphone that you're using. So it is also flexible in that way as well. Okay, so I'm going to pass the intermediate slide. So this is the algorithm which we implemented. So the first part refers to the ping pong array. So that can be a generic pre-processing block. Whichever way you obtain the particle velocity and pressure signals does not matter too much. Then you go to time frequency domain by short time Fourier transform. Then you multiply pressure with particle velocity components. You calculate complex intensity. Then you take the real part and calculate the active intensity. Then you carry out direction of arrival estimation in time frequency domain. You can estimate the direction statistically as well. And then carry out virtual beamforming in any directivity pattern that you wish. It may be a cardioid, or it may be a second order, third order pattern, which is a maximum directivity factor pattern or maximum front to back ratio pattern. Then you go back to time domain and you obtain a signal which amplifies the direction that you pointed your virtual beam to. So some applications, I think we are substantially over with the theoretical side, which is good. So direction of arrival estimation with open spherical arrays. We measured acoustic impulse responses in 3 different environments. Our lab, which has a very low reverberation time, 80 milliseconds, we measured 12 directions. In a meeting room, which has 780 milliseconds reverberation time in 12 directions. And we made measurements in a lecture hall in our institute. And we convolved these impulse responses with anechoic speed samples to obtain the test signals. And then we try to find the directions of those signals, basically, directions of these synthetically generated test examples. So in all cases, the highest azimuth angle estimation error was 10 degrees, and highest elevation angle error was 6 degrees. So here is the measurement which we carried out in our lab. And the blue lines show the ideal case, which will never be attained anyway. But the red one shows our measurements. You see that the azimuth angle in this case is between -4 and 8 degrees, and the elevation error is between -4 and 6 degrees, which is a good result, actually, considering the simplicity of the algorithm. So for the meeting room, you can actually, I cannot zoom in, unfortunately, but yeah, it's at the middle of the meeting table. And you see, again, the measured azimuth and the ideal case with blue and measured in red, and the errors are within -10 and +10 degrees. And you see the identified directions of sound sources in red and blue. Blue corresponds to the actual direction, and red corresponds to the estimated direction, which is a good representation, I guess, of the results, which is more informative than the one on the left, at least. And here is the 48 positions that we measured in a lecture hall. You see that most of the cases, well, in all of the cases, it's quite close, and the error is between -11 something and +7 something, I guess. So source separation with open spherical microphone arrays. I don't want to go into details. That would be more in the domain of signal processing, probably. But in a paper in 2016 ICASP, I used a quaternion representation of particle velocity signals, and that allowed me to separate different sources from the resulting distributions. So again, not too much details on this one. For those who are interested, it's in this paper. I'm going to make this presentation available through my website, so please do check. And here is a graphical depiction of what happens. You have a mixture. Say, in this case, you have two sources, a female speech and a male speech signal from different directions. Female speech is the target, so we're trying to separate that. And male speech is the interference. So you see the mixture at the top. The target is the red one, and the separated signal, the female speech, is at the bottom. And for those of you who are familiar with source separation algorithms are typically evaluated by signal to interference ratio. And in this case, it was rather high, up to 55 dB. Those are big values. That's because SIR is a good representation of the source separation capabilities of your algorithm, but it doesn't tell you too much about the quality of the result that you get. So it's just some metric, some number. So when you listen to that, it's not good as 55 dB SIR, but you still get a very good separation. So that is, for instance, it is possible to use this algorithm for hearing aids. That is one possibility. It can clearly pick out speech in the case of multiple speakers in the same environment, which are active at the same time. Then rigid spherical microphone arrays, DOA estimation. One of the simplest methods to apply for this purpose is steered response power maps. That is, okay, I'm going to give you another analogy from real life. You have a torchlight, you're looking for an object, and you go into a room, a dark room, and you look around. You scan the room by using the torchlight. And let's say I'm looking for that chair over there, and just, oh, okay, that's the chair. So that is what SRP is about. You scan the whole 3D environment, your room, your dark room, by using your torchlight, and find the object that you're after. So by this way, it is possible to localized sources. It's not ideal, by the way, but it can give you an idea about the directions of sound source. Again, another measurement from our lab. For some reason, I guess that is because a panoramic capture was used with the iPhone. The heights of these different loudspeakers do not look right to me. Maybe that's perspective, I don't know. But some of the loudspeakers were 16 degrees above and some others were 16 degrees below the horizontal plane. So you see the steer response power maps. So again, that's your torchlight which you use to find out your chair over there. So this is your chair in this case, obviously. That's your sound source. There are some problems with SRP. As in the real life example, you don't go into a room and haphazardly look at every direction with your torchlight. You typically have an idea about where your source is, where the object is. The chair cannot be, for instance, anywhere. It could not be floating in the air. So we developed, okay, I'm going to talk about this later. The second important problem is computational cost. Okay, I haven't talked about the first important problem. Multiple coherent sources cause a problem. So you have multiple peaks there which may overlap. Okay, so that's one big problem. And computational cost is a problem. That is you looking at everywhere inside the room, although you know that it's somewhere at that corner, for instance. And the resolution. So resolution may not allow you to localize multiple sources, even in the incoherent case. There are some algorithms which have achieved success especially with incoherent sources like speech, but not with music, most of them. The name of the first algorithm is EB-Esprit, that at least partially solves the multiple coherent source problem, but it's computationally costly. And another one is eigenbeam music, multiple signal classification. That's an algorithm which is defined for spectrum estimation being ported to this problem, basically. And pseudo-intensity vector. These three methods have been the more mainstream methods being used in this application. And a common problem with all of these is the necessity to know the number of sources. If I have 4 sources, and if I know that there are 4 sources, they work perfect. They can tell you about the directions. By the way, I'm talking about speech sources, not music, for instance. Not musical sources. Let's say if you have 4 musical instruments playing in unison the same thing, then these fail as well. So that's not an option for these algorithms. There are several extensions to these algorithms. For instance, DPD music uses a test called direct path dominance. It looks specifically at time frequency bins for which a single source is active. So it goes and finds that time frequency bin and calculates the music spectrum on that time frequency bin exactly. Say there are other methods, extensions to pseudo-intensity vector approach, subspace PIV, augmented intensity vector approach, etc. So we developed a new algorithm very recently, which, as opposed to the original SRP, looks at directions of interest, which is calculated by a concept called the information gain. So we deconstruct the spherical surface into smaller subparts, which we search for a source, sound source, and we are able to carry out steer response power map analysis without the computational cost which is associated with that. So we carried out a set of measurements in a classroom in the institute, 120 measurements with the EigenMic, EM32. And here are the results for speech and violin. In violin, by the way, speech is pretty much the same for all our algorithms which you can get. All state-of-the-art algorithms will give you very good results in terms of sound source localization, direction of analysis estimations. But in the violin case, we used 4 tracks from Mahler's First Symphony, 4 violins, playing in unison, the same phrase. So if you yourself were at the middle of that room, with 4 loudspeakers playing the same material, you may possibly not be able to locate those sources because they're playing the same thing, essentially the same thing. So that's a scenario which links back to the figure which I showed you with the quartet playing. So they may be playing in unison. How do you find out their directions if you wanted to extract those objects from your recording? So even in the case that you have coherent sources as such, we have very good less than 2-degree direction of arrival estimation error, which was very exciting for us. I mean, we weren't expecting such good results, and the computational cost is low as well. So we are quite excited about this. So it's been submitted. So we're waiting for the results from IEEE audio transactions. And in summary, so we talked about spherical microphone arrays, which provide distinct advantages. Now, for now, the idea is to record the whole 3D environment, and these arrays give you that opportunity. So you can position your microphone array, record the whole sound field without the need to consider about the mixing that you're going to do at the very end before you release. So those are very flexible in that sense. They have both theoretical and practical differences, these different types of arrays. Rigid arrays are typically used with the spherical harmonic decomposition framework. Open spherical microphone arrays are more suitable for applications involving the energetic analysis like the intensity, which I talked about. And these arrays, I believe, are likely to be more mainstream in the coming years due to the development of miniaturized, high-quality MEMS microphones. Even today, especially if you remember the example from Danish Technical University, the black rigid spherical microphone array, that was using MEMS microphones. Now, the problem, let's say, the problem which needs to be addressed by the producers, manufacturers of those MEMS microphones is to get capsules which have a very good quality output so that it can be used in professional audio applications. So that is the main problem right now, but I believe that will be solved in a short time. So it's going that way. Just at this point, I need to mention 2 very good projects. One is mainly involving the UK, this community as well in that sense. A European project called Orpheus. I was here to review that project, which provided amazing results. I believe the AES British section should invite those people to talk to you. Okay, I know you have links with BBC, obviously, but these people should come and present their results, or you should meet somewhere and see their results. They're working together with Fraunhofer, the new MPEG-H standard. They're implementing that amazing project, which is about object-based audio. So that's also one of the problems that they face, how to record the sound field and how to extract objects. And another project is S3A, which is 3 universities which carry out audio-related work, Southampton, Surrey, and Salford. So that's also a very exciting project. So I believe these projects will benefit from spherical microphone arrays as well as spherical microphone arrays benefiting from the research coming directly from out of these 2 projects, as well as mine. So I have a project going on as well, so I need to mention that one as well. So any questions? Oh, thank you.
Thank you. Thanks, Huseyin, for the very nice talk. It's just recorded, okay. So yes, I've come across various of these topics, so it was very nice to see them all together. So I have more than one question. The first one is, you mentioned something about the startup building new spherical microphone arrays. So I was wondering, what do you think is the scope for reducing the price of spherical microphone arrays, and where does the Eigenmic costs £20,000, so that's only very few people can afford that.
Yeah, go ahead, sorry.
And where does the majority of the cost come from? Is the problem mostly that you need very sensitive capsules, or is it the processing? And in general, as I said, where do you think that one can save more money? That's the first question. The second question is, as far as I remember, you have to invert those Bessel functions at some point, which means that you're going to boost the low, the self noise, low frequency self noise. So the question is, how applicable are spherical harmonics, spherical arrays in the audio engineering society, considering that perhaps the majority, the most important objective is audio quality rather than spatial resolution?
Now, okay, the answer to your first question, well, I have no links with that company producing that spherical array, but I'm waiting for them to release that so that I can go and buy it. And the price was, if I'm not mistaken, 900 euros or something like that, which is reasonable.
The first ones arrived in the UK last week.
Ah, okay, that's great, that's great. So, can you give me the address, please? Okay. Okay. So, Zilia. So they are reasonably low cost, I think. But again, I have no idea about audio quality which you get out of Zilia microphone arrays. The cost lies with high quality capsules. Obviously, the processing is less of an issue, I believe, because I believe Zilia as well as MH Acoustics develops those algorithms in-house, and it's mainly the IPR which they are selling. So obviously they need to get the microphone capsules right, get the microphone array as a viable product, and that's what they're doing, and that's why they're selling it for 20 grand. But obviously, they will have to find, or they will have to reduce their price, or find other ways of capitalizing on their IPR to compete with the likes of Zilia in the near future. The other question was about self noise.
Self noise.
Yeah. Okay. So I believe if you that'll be slightly more technical, but if you increase your sampling rate, then all your KR values will shift towards the low frequencies. So you'll be able to capture your sound field better without a significant level of white noise amplification or sensor noise amplification. So that may be one option. Otherwise, it's just an inherent problem with the spherical harmonic exposition. So you cannot really do anything about it unless you find some adaptive algorithms which can possibly get rid of the noise in the first place. But that's open to research, I guess.
That will work for high frequencies, but not for low frequencies. Like you wouldn't solve the problem of low frequencies by increasing the sampling rate, or
if you increase okay, let me think. KR will be higher, so you're compressing your functions, your BR functions towards the low frequencies, right?
Spatial sampling. No.
Yeah. Sorry, I'm not getting it right.
Spatial sampling rate. Was your question about, were you assuming temporal sampling?
No, I was talking about temporal, actually. Sampling rate, when I say temporal sampling rate. So if you use a higher sampling rate, 192 kilohertz, for instance, you'll shift everything towards the low frequencies. It's KR, right?
Yeah, but the frequency is the frequency of interest, isn't it? Not the sampling frequency.
Yes, that's right. So let's discuss this later. Okay, I'm not quite sure if I'm getting the question right as well. Okay, sorry.
Very interesting talk, thank you. In many applications, the sources of interest and many of the reflections are all close to a single horizontal plane. Is there any sense in using circular arrays or other two-dimensional arrays rather than spherical ones? I can see there's obvious mathematical benefits in the symmetries of the sphere, but has there been significant work done on circular arrays?
Yeah, of course. Actually, the project which I just mentioned, Orpheus, they're now using a prototype developed by, I guess, Fraunhofer, a circular array. So it's always possible. I mean, as long as your sources of interest are in the horizontal plane, then why not? I mean, using a circular array would work as well as a spherical array. But if you want to capture the whole 3D, then it would be wise to use a spherical array, I think.
Yeah, you can get you can get a hemisphere using a circular array.
Of course. Yeah, that was one idea which was explored by Maryland, Ramanid Roy Swami. They used a bowling ball and
Right.
they drilled holes on it and positioned capsules and put it on the table.
Right. Yeah.
So something like the mirror image of your bowling ball appeared. That sort of understanding, basically. So on a rigid planar baffle.
Is there an equivalent formulation of the? Is there an equivalent to the spherical harmonic formulation? Is there cylindrical harmonics formulations there?
Yeah,
Yeah.
sure.
Okay. Thank you.
Hi. First question. You're confident, or no? You believe that high quality MEMS capsules are on the way in?
Let's say I hope that they are in the way in. I'm not confident at all.
I'm not sure there's a commercial case for people to make them. I know that the early work on MEMS capsules was explorative and can certainly confirm that there are no limits to making. There are a few practical. It's entirely possible to make high performance MEMS capsules, I believe. But commercially, why would anyone of their current makers of MEMS capsules stray into the prosumer territory, I wonder?
Yeah. Mobile device manufacturers are looking at ways to capture 3D video and audio by using devices which can fit in your pocket. So if you can design a small enough microphone array, spherical microphone array, which could sit on top of your phone and in your pocket, obviously, then it would be a big gain for them. So the financial, economical gain from that for a company which would develop such miniaturized elements would be great, I think, in that sense. And I know of Knowles has miniature microphones, which we tried using in our work before. Really small. I mean, actually, they arrived at my department, and the person responsible with these transactions came to me and said they just sent the cables, not the capsules. They're so small. Okay, so they are not MEMS, but they are small enough which can allow you to do certain stuff with miniaturized arrays, possibly. Obviously, there will be some other problems, but I believe the problems that we see as unsolvable right now will be solvable in 3 to 5 years. So I'm at least confident about that.
Okay, and then if I may, another quick question. Sparsity techniques seem to have a role in the decomposition. I believe some people have explored that. Can you make some comments on that?
I haven't read about that, so I'm not in a position to comment, really. Okay, sorry about this.
Very interesting talk, thank you. A couple of generalized points. Rode are now have announced a video mic sound field to go on top of a camera. So a smaller...
So which company?
Rode in Australia have announced the video mic sound field, which will hopefully be in production soon.
Yeah.
At least that will be a standardized sound field, of course. I was, in terms of spheres and first order ambisonics that we've had for 30-something years now, and love it to death. A couple of points. One is, as we're going to make smaller and smaller items, and therefore they're going to be more and more mobile, we're hitting this critical point that directional data of where the thing is pointing is becoming a first order data type alongside video and audio.
Yeah.
And if you're if you're going to start wanting to mix video and audio from multiple sources, multiple camera angles, multiple microphone arrays into a scene, especially if you're going to want to render it into more of a VR environment, so you're rendering at runtime, then we need to have directional data as a first order data type. On a more generalized point, when we're talking about spherical arrays here, we're all obviously very familiar with A format and B format, and how we use that and how we get to it from a first order sound field. How do you think these spherical microphones are going to render to a format that we can actually practically use moving forward? It's great in a theoretical environment. It's great in an acoustics measurement space. But how are we going to actually take this, record something, store it in a way that we can then use it moving forward? I would be interested in your thoughts on that.
Okay, in my lab, we haven't yet tried higher order ambisonics with Eigenmic, the rigid spherical microphone array. So I cannot really give evidence about my own, listening evidence about this. But what I heard is that people dislike higher order ambisonics recorded using Eigenmic EM32. That is, I guess, reasonable because you're introducing a sphere in your field and you're recording by using still lower quality capsules than the original sound field. So those are given. In a more practical setting, I'm going to give you an example from the project which I reviewed yesterday. They're using it to capture the diffuse field. So they can capture information about the properties of the enclosure by using this array, or they can use it to find out about the distances of sound sources which are recorded using spot microphones. So you can record your object using a spot microphone and you can find out the distances of these sources by using your rigid spherical microphone array recorded signal plus the spot microphone and get the distance data as well.
So do you think, one final point, do you think the spherical arrays and what we can do with them and what we will be able to do with them in the future, you're talking about analyzing the acoustics of a room, etc., and that is a fascinating new set of things that we can do, but it isn't related to B format and music and recording and capturing traditional ambisonic type things. Do you see them as two not related but different spaces, or do you see them as still very much overlapping?
I would disagree with this because the original, the photo that I showed you, that was recorded by using a DPA 5100 5.1 microphone, and Neumann had a zoom as a backup, the EM32 two Rhodes pairs. And well, Eigenmic, I don't remember if I mentioned it. So the idea is that we will be checking, and that will happen in the next 2 months, I guess, whether it is possible to extract those different instruments from the mix and get some result which is comparable to, say, for instance, what you would record with the DPA 5.1 microphone.
Okay.
So we will see. We haven't yet tried it. Okay. But the idea is to extract the sources and remix them in such a way that it would give the results which are comparable to a microphone situated, say, away from the scene, at a different position in the concert hall. So again, I cannot, we haven't tried it, so I cannot tell. But hopefully sometime we will get good results and publish it. So, but that's a hope. So again, no guarantees. No? So I have one more slide since. Okay. So since this is the Christmas lecture, have a Merry Christmas and thank you very much for inviting me. Thank you.